Hey there, here's one of these tricky Coulomb's law problems. We're trying to find the magnitude and direction of the net force on B. And you start off pretty easy here. We're just going to use Coulomb's law, which is F equals K Q1 Q2 over D squared. Um, and there's two things that are exerting a force on B. A is exerting a force on B, and C is exerting a force on B. So we need to figure those forces out one at a time. So let's do the force between A and B first. So K is 9 times 10 to the ninth. It's always that number. Charge A, it says, is 2 microcoulombs. And here's one of the things you have to be careful about. When you put numbers into Coulomb's law, they have to be in coulombs, not microcoulombs. So I'm going to do 2 times 10 to the negative sixth because, and this is good to remember, a micro really just stands for times 10 to the negative sixth. They literally mean the same thing. You can just always replace the symbol micro with times 10 to the negative sixth. Charge B is 6 times 10 to the negative sixth. The distance between them is 3 centimeters, but here's another spot where you have to be careful because when you use Coulomb's law, you have to put in meters. And the conversion there means you have to take centimeters and divide by 100. So that's 0.03 meters. So if I put that in the denominator, don't forget to square it, pop that into my calculator, and I get 120 newtons. Technically, it's plus or minus 120 newtons because each one of these charges feels a force and one of them gets pushed one way and the other one gets pushed the other way, but not a big deal. Now let's do the force between B and C. So again, K is 9 times 10 to the ninth. B is 6 times 10 to the negative 6 coulombs. C is 5 times 10 to the negative 6 coulombs. Again, it's got to be in coulombs, not microcoulombs. And that's because the number for K, 9 times 10 to the ninth, is based on coulombs and meters. So everything has to be in coulombs and meters. So now I'm going to divide by the distance between B and C. It's 4 centimeters. But again, I have to divide by 100, which gives me 0.04 meters. Square that. And you do that on your calculator, you get 168.75 newtons. Okay, that's probably the easy part. Here comes the trickier part. The trickier part is putting these forces together when they're at a right angle like this. My suggestion is first, let's take this 120 newtons and let's draw that into the picture. Now that's the force between A and B. So if we look at this diagram, A and B are both positive, so they're going to repel each other. So that force looks like this, 120 newtons. Now our other force, I'll do this one in green, is 168.75 newtons. That's between B and C. They also repel each other. But to try to make an accurate picture, since 168.75 is bigger than 120, I'm going to draw a bigger arrow. So there they are repelling each other. And what we're ultimately interested in now is the total force on B. Now, logic would tell you that if something pulls down and to the left, the object's going to move diagonally that way. And that's correct. And we can get a precise value on that if we draw a little rectangle here. And actually, I'm going to redraw this just so it's more clear down here. So here's B. Here's that 120 Newton downward force. Here's that 168.75 sideways force. And if you want to accurately draw the net effect of those two things, think of this as a rectangle. So 120 newtons is one side of the rectangle. I'm going to draw an identical side over here, the same length. Rectangles have the same length on opposite sides. Same thing down here, same length as what I drew up here. And then it turns out the way that the picture works, the diagonal of that rectangle is exactly the direction that the net force would point. This is the net force here that we're looking for. And again, since it's a rectangle, that means that this side is also 120 newtons, and this side down here is 168.75 newtons. So if we want to find the magnitude of this, the length of this, the size of this, it's just a Pythagorean theorem problem. And in math class, I know you would probably write c squared equals a squared plus b squared. In physics class, we call the diagonal the resultant, so r squared. And then this side is the x side squared, and this side is the y side squared. So putting in those numbers, the x side is 168.75 squared. The y side is 120 squared. Take the square root of that, and that gives you the magnitude, one of the parts of this question that we're looking for. And I pop that into my calculator, I get 207 newtons. So that's the magnitude of the net force. Now, to find the direction, what we're really talking about is an angle. I like to measure the angle from the nearest x-axis. So what I'm going to be finding out is how many degrees below x this is. So x points that way. This is going to be how many degrees below x. And we know two sides of this triangle. We know the opposite side and we know the adjacent side. And so we can use tangent because the definition of tangent is opposite side over adjacent side. So the tangent of this angle that I drew in this picture, well, you can see I drew it coming from the x-axis. So that's what it's adjacent to. 168.75 belongs on the bottom. And opposite, we have 120. So that's what the tangent's equal to. To find out what the angle is equal to, you have to do the inverse tangent. So we're going to do the inverse tangent of 120. Sorry about that. 120 over 168.75. And when you pop that in your calculator and you want to make sure your calculator is in degrees, you get 35.4 degrees. So that's the other part of the answer to this question. And as long as you have your picture labeled with that angle on it, I'll know that that's the angle that you're talking about there. Okay, so hopefully that helps, and good luck with solving these problems.